Okay, so today you are going to cover, oops, 4.4 on complex numbers, and then you're going to do assignment number 21 for homework. Now, since I am not here, I just want to remind you that I posted solutions to assignment number 20, so you can check those. All right, so let's get started. Okay, so we are on page 10, and we're going to take a look at what are called complex numbers. And so in order to talk about complex numbers, we have to talk about imaginary numbers. Okay, so obviously up until now, all the numbers you've encountered in mathematics have been real numbers. Basically, anything that's a real number, you can locate it on a number line. So if we think about 1.5, that's a real number. I can locate it on a number line. Even pi, which is, approximately 3.14, we can find it on a number line. However, we do have something called the imaginary number I, okay, that is not located on a number line. And that's basically useful when we're trying to understand quadratic functions that do not have any real roots. So in other words, when we did the lesson where we're talking about the roots of the function, and I gave you some examples where, if you have a parabola and it does not cross the x-axis, it does not have any real roots. However, it will have imaginary roots or complex numbers for solutions. So imaginary numbers, where are they used? They're used in electricity and electrical engineering. They describe electrical currents, also used in physics, all right, modeling periodic motions such as light waves. So in Algebra 2, we're just going to get kind of the basics. And then you'll get a little bit more of that in pre-calculus. Okay, so let's talk about imaginary unit I. So the imaginary unit, we use the letter I, and I is equal to the square root of -1. And so we can have different types of imaginary numbers. So you might have what looks like a coefficient in front, like 5i. You can have a -2/3 I. You can have an I times the square root. Generally speaking, I'm not going to write it as square root of 3 with the I after, because I don't want to accidentally put the I under the square root. So whenever we have a square root involved, I like to put the I first. Okay, so let's take a look at example 1. We're just going to simplify. And so the first one says square root of -9. So we can actually think of this as the square root of -1 times the square root of 9, kind of pulling out that square root of -1 to recognize that that's our imaginary unit I. So it's I times square root of 9, which would be 3. And so we can just write the final answer as 3i. Next one, I see square root of -64. So again, you can think of that as -1 times 64. So just think square root of 64 is 8. And then we multiply it by the imaginary unit I. Okay, now I have square root of -18. So what I would like you to do is simplify square root of 18, and however you like to do that, so maybe we'll do that on the side here. So you could do a factor tree, or I can think, oh, what's the largest perfect square that goes into 18? That's 9, so that would be 3 root 2. And so now when I write my answer, remember how I had talked about over here where we put the I first? I'm actually going to put it between the 3 and the square root of 2, so it's going to go 3i root 2. Okay, so again, all of these that have a negative under the radical mean I'm going to have an I in my answer. So again, here I have square root of -125. So maybe on the side here I can just simplify square root of 125. So that'll be square root of 25 times square root of 5, which will give us 5 root 5. So then if I'm also considering that negative, it would be 5I root 5. Okay, so next what I want to look at is what happens when we have powers of I. So obviously I to the first, that's just our imaginary unit I. But take a look at what happens if I have I squared. So think about this for a minute. If I have I squared, remember what I is equal to? I is equal to the square root of negative 1. So if I have the square root of negative 1 and then I square it, remember the square root and the square cancel each other out, right? These are inverse functions. And so I'm just left with what I had underneath. So that's how I get negative 1. So I squared is always going to be equal to negative 1. Okay, so think about I to the third. Now what do we have? We have basically square root of negative 1 times square root of negative 1 times square root of negative 1. Well, that's going to give us negative 1. And then remember, this is our imaginary unit. So negative 1 times I, which will be negative I. So I to the third gives us negative I. Another way you can think of I to the third, just kind of on the side here, I could also break that up into I squared times I, right? Remember adding exponents, so we can also go the opposite direction and take I to the third and rewrite it as I squared times I to the first. Well, I just showed you that I squared is negative 1, so that's another way of looking at getting that same result. I to the fourth. Okay, so again, I could think square root of negative 1 times square root of negative 1 times square root of negative 1 times square root of negative 1. Or I can think of this as I squared times I squared, right? Kind of thinking of, right, I squared plus I squared, we would add the exponents. Well, what would that give us? That would be negative 1 times negative 1, right? This would be negative 1 because I squared was negative 1. And so I to the fourth is always going to equal 1. Okay, continuing in that pattern, if I have I to the fifth. All right, so, well, if I know I to the fourth is equal to 1, it's really easy to just break I to the fifth into I to the fourth times I. So that's going to be 1 times I, which equals I. So I to the fifth is equivalent to just I to the first power. Okay, I to the sixth, I can think of that as I to the fourth times I squared. I to the fourth, again, we just proved that that was equal to 1. And then look above, right? What do we get for I squared? It's negative 1, so this would be negative 1. I to the seventh. I can think of this as I to the fourth times I to the third. I to the fourth is 1, and right here, I to the third was equal to negative I. So I to the seventh is negative I. I to the eighth, I can break that down into I to the fourth times I to the fourth. So 1 times 1 gives us 1. Okay, I to the ninth. All right, so think that's I to, again, what we're thinking, and again, if you look at this first column, you'll notice a pattern here. The second column, you should be noticing a pattern here, third, and the fourth. So when I have I to the ninth, basically I have I to the fourth times I to the fourth times I. So I to the ninth will be just I. I to the 10th, I can break it down this way, and that will be negative 1, because I to the fourth is always going to be 1, and then I squared is negative 1. I to the fourth times I to the fourth times I to the third, That's our negative I. And finally, I to the 12th is going to be I to the 4th times I to the 4th times I to the 4th, or you could do I to the 4th to the 3rd power, and we get 1. So notice all the possibilities. We can either get I, all right, we can get -1, we can get negative I, or we can get 1. And notice it's all based on what I think is easiest is think about I to the 4th, right? So any multiple or any power that has a multiple of 4 is always going to be equal to 1. So take a look at 53, right? I know I to the 53. So if I want to break this down, I think, okay, well, 4 goes into 53 how many times? It goes in oops. It goes in 13 times, and 1 is the remainder. Another way to look at this is this would be I to the 52nd power times I to the 1st power. And because 52 is a multiple of 4, this is just going to be 1 times I, which equals I. Again, you can just kind of focus on when you divide what's your remainder, and that's going to be the power of I that you end up with. So looking at the next one, 4 goes into 115. Let's see, it goes 2 times. We get 3 as the remainder. So this is going to be equivalent to I to the 3rd power, which is negative I. 74, I can divide that, or we can just look, I recognize that I to the 72nd power, 72 is a multiple of 4, so that has to be 1. And then I have times I squared, so we get -1 for the result. So again, it's always going back to that power of 4, and then what do we have left over? Okay, let's look at some simplifying. So example 3, we have 3i times 4i. So when we're first evaluating these, we think of I as an exponent, or not an exponent, excuse me, a variable. So I'm going to have 12i squared, but I don't want to leave any powers of I. So I squared, well, recall on the previous page, was -1. So it's 12 times -1, so that gives us -12. Okay, next one. So I can, what I want to do is simplify each radical first, and then we'll multiply. So looking at square root of -12. So 12 would be 2 root 3. But I have a negative in there, so I'm going to make that 2i root 3 times, and then I have a negative here, so that's I root 2. Now I'm going to combine, so I'm going to multiply. So I have 2i squared times the square root of 6. I squared is -1, so I get -2 root 6. Okay, so you want to definitely write it in terms of I first, and then you're going to multiply it out. Okay, next we want to take a look at the square root property. So prior to this, when we were solving, we were using factoring method. So today we're going to be doing the square root property. So this is when we have x squared equal to something, and we take the square root of both sides. And then keep in mind, technically what we get is we get the absolute value, which means we get a positive and negative value. Usually when you learn this in Algebra 1, your teacher might skip this whole absolute value process, and they'll jump right to, oh, it could be positive or negative a. But technically that's because there is, when you take the square root of something squared, you get the absolute value of what's inside. Okay, meaning what's inside could be positive or negative. Okay, so let's solve. First thing we want to do is we want to isolate x squared, so I'm going to divide both sides by 4. We get x squared equals negative 25. Now I'm going to take the square root. Now, up until this point, you would generally say, oh, that has no solution, right? It has no real solution. It has an imaginary solution. So it's going to be x equals, I see a negative under the square root, so that's going to be 5i plus or minus 5i. Next one, again, I want to isolate the x squared first. So subtract 20 from both sides. Divide both sides by 5. We get x squared equals negative 4. Take the square root. We get x equals, and that's going to be plus or minus 2i. Okay, so far what we've been looking at are called pure imaginary numbers because it's just been I or it's been I with a coefficient. Complex numbers is a combination of a real number and an imaginary number. We write these in the form of a plus bi. So a is what we call the real part, and bi is the imaginary part. They are not like terms and cannot be combined. Okay, so this next part is going to really look pretty basic here in terms of simplifying. All you're going to do is you're going to combine the real terms and combine the imaginary terms. So in other words, I can combine the 3 plus 4, and then I'm going to combine the 5i and the minus 3i. And so we're going to write 7 plus 2i. Next one, I'm just going to distribute, so let me just write that first binomial down. So 6 minus 5i minus 3 plus 2i. And so I can combine 6 and the minus 3. Gives us 3. Minus 5i plus 2i, that's going to be minus 3i. If you want to pause and try the next two on your own, you can do that. Or you can just keep following along. The next one I'm going to do is distributive property, so that's going to be 6i minus 15i squared. Now remember, I squared is negative 1. So that really turns into a 6i plus 15. Now, I know this might seem like an unnecessary step, but when it says simplify, you always want to leave answers in the form a plus bi. So we always want to put the imaginary part second, and that has to do with actually how we graph complex numbers in the complex plane. So I'm just going to rearrange this for the last step. So I'm going to put 15 plus 6i. Okay, next one, we have 2 FOIL. So I'm going to multiply 5 times 3, so that's going to give us 15. Then I'm going to multiply 5 times minus I, so that would be minus 5i. Then negative or minus 6i. And last is going to be plus 2i squared. So I have 15. I can combine the middle two terms. That's going to be minus 11i. And then remember, what is I squared equivalent to? It's equivalent to negative 1. So that would actually make that into a minus 2, right? 2 times negative 1 would make that a minus 2. And then I can just combine that with that first term. So that's going to give me 13 minus 11i. Make sure that I do have it in the proper form. It's the real part and then the imaginary part. Okay, last page, dividing complex numbers. Okay, so remember, what is I equal to? I is equal to the square root of negative 1. So one of our rules for writing numbers in the proper form is we can't have a square root in the denominator. All right, so we cannot have I in the denominator either because it's technically a square root. Okay? So I'm going to show you some ways to get rid of I. I'm going to jump down here to example 6a. I have I in the denominator. Now, just a quick side note. Let me just remind you back when you learned this perhaps in algebra or geometry and you had an answer like 2 over root 3, the only way to get rid of the root 3 was to multiply the top and the bottom by that same radical. So that would be 2 root 3 over 3. And we would leave our answer like that. So what do we notice? Whatever was in the denominator, right? I multiplied the numerator and denominator by that to eliminate the radical. We're going to do the same thing here. So if I have I in the denominator, I'm going to multiply the top and the bottom by I. So that's going to give me 2I over I squared. But what's I squared equal to? I squared is equal to -1. So my final answer is just going to be -2I. So just kind of divide 2I by -1 to make that -2I. I have here, make sure to leave the result in the form a plus bi. I didn't have a real part, so this was just a pure imaginary number. Okay, now I have 2 minus I in the denominator. What we are going to do is use what are called complex conjugates. So if I have a plus bi and a minus bi, and I take the product, meaning multiply them, it will always result in a real number. Okay, so let me take a look at this. So if I have 2 minus I, what we call the conjugate would be 2 plus I. So I am going to multiply 2 plus I to the numerator and denominator. What do we get in the numerator? We're going to distribute. We will get 6 plus 3i over. All right, well, if we do FOIL here, right, we would have 2 times 2 would be 4. What happens when we multiply conjugates? Take a look at when we multiply the outside. That'll be plus 2i. Inside is minus 2i, so those will always cancel. So technically, we just really have to multiply the first and the last, so that'll be minus I times a plus I, so that'll be minus I squared. And then, so we have 6 plus 3I over, now remember that's -1, so if I have 4 minus -1, that's going to be a 5 in the denominator. Okay, the last step here, remember how I talked about a plus bi is the form we need to have it in? We are going to break this up into 6/5 plus 3/5 I so that it is in that correct format. So it has the real part is 6/5, the imaginary part is 3/5 I. Okay. Again, if you want to pause it and try the next 2 on your own, otherwise I will keep going. Here we're going to multiply. So if 3 plus 5i, I'm going to multiply by 3 minus 5i in the top and the bottom. In the top, I'll get -6i plus 10i squared over, I'll get 9 minus 25i squared. In the numerator, this will be -6i minus 10, again, that I squared is -1, so it basically just changes the sign. In the denominator, I'm going to get 9 plus 25, because again, I squared was equal to -1, so it's like minus 25 times -1, that makes it plus. Okay, almost done. I am going to just switch the numerator, so it's -10 minus 6i over, and that's going to give me 34. Again, not very pretty. Unfortunately, we're not quite done. We still need to keep going further because we want to separate it so it's clear that we have the real part and the imaginary part. So -10 over 34 will reduce to -5/17, and then 6 over 34 will be minus 3/17 I. Next one, again, we always work with whatever's in the denominator, so it's going to be 1 plus I, 1 plus I, and it looks like I have to do FOIL in the top. So I'm going to have 2 plus 2I plus I plus I squared. And the denominator, I just get 1 minus I squared. In the numerator, I get 2 plus 3I minus 1 over, that'll be 1 minus negative 1, so which gives us 2. So I have 1 plus 3I over 2, and then I'm just going to rewrite that, so it's 1/2 plus 3/2 I. Okay, last one, find the values. So complex expressions. So basically, if these two are equivalent to each other, then that means A equals C and B equals D. So here I have an equation. It says 5x plus 1 plus 3y, or plus 3 plus 2y, I equals 2x minus 2 plus y minus 6 times I. So basically what we want to do is we want to make the real parts equivalent and the imaginary parts, or their coefficients, equal. So I have 5x plus 1 equal to 2x minus 2. So that's going to be 3x equals negative 3. X equals 1, negative 1. And then we're going to set 3 plus 2y equal to y minus 6. So we get y equals negative 9. Okay, and then you can spend the rest of the time working on your homework assignment, which is here, assignment number 21, page 250, 19 to 41 odd, and so on.